Glad to say that we've got Professor Luciano Lavagno here with us. He did his PhD at UC Berkeley, 10 points to whoever can guess what year he graduated in, from Politecnico di Torino in Italy. And he's co-authored a couple of world-famous books on asynchronous circuit design, a book on hardware, software, co-design of embedded systems, the CR. This is a long list. This is a very long list of accolades.
I didn't intend that to be read. Sorry.
No, I'm just messing with it.
I just picked it up.
Yeah.
I pasted it.
I'll put the bio down. So
Yeah.
clearly done a bunch of important things.
Absolutely.
Luciano and I actually got linked up through one of your PhD students, Fabrizio. So there's a bunch of neuromorphic people in the crowd. So if you've seen Fabrizio's name in the open neuromorphic Discord server, he brought us two together, and he's been doing some projects that combine digital design, high-level synthesis with neuromorphic computing, spiking neural networks. Luciano flies back and forth every 3 days or every month between Italy and the Bay Area. He does work with Xilinx AMD as well. So he's more expert than me at Santa Cruz. So without any further ado, take it away.
Thank you very much, Jason. And hello, everyone. UCSC has a special place in my heart because this is where I gave my first conference presentation. I think it was around 1991, a long time ago. But that was the beginning of a very happy career. The presentation today is titled Mix and Latch, and it is about how you can finally use all 4 types of sequential logic elements that you all learned about in your first digital design class. Positive edge flip-flops, negative edge flip-flops, positive level sensitive latches, negative level sensitive latches. People have figured out over the years how to use 1 or 2 of them together in the same design, and they got so far. We managed to use all 4 types, and we managed to get way beyond in terms of what you can achieve in performance, as I will show in this presentation. Please stop me at any time. I don't know the background of any one of you except for Jason. And for this reason, stop me if I say something which is not clear, you'd like some more explanation about. I try to keep the talk as easy to understand as possible. So the goal of this work is to improve digital circuit performance, clock frequency, by selecting the kinds and choosing the locations of sequential logic elements starting from an existing digital design coded by a human or by high-level synthesis in synthesizable Verilog or VHDL, with an important constraint that wherever the designer had placed initial flip-flops, we will still keep one memory element, could be a flip-flop, could be a latch, in that same location. This will be very important to ensure verifiability and testability of the resulting circuit. And this is a key differentiator from most past work. So just in summary, in a circuit design, you are trying to make data fly through combinational logic from a launching memory element to a capturing memory element. The data can start running when the launching memory element opens, and it has to get to the destination by the time the capturing memory element closes. So you have, like in a race, a gate that opens, you run through a course, and then you have to get to your destination before the terminating gate closes. Otherwise, there is a miscomputation. Moreover, there is a second constraint that you don't have to go through too many gates, open gates, at the time in every clock period, since this is a synchronous system where everything is controlled by one general clock that tells every flip-flop, every latch in the system when they need to open and close. We want every runner to go through one memory element exactly through every phase. So if they have a short path to go, they shouldn't be able to go through one and go through the next and be captured by the second one. So these constraints normally have to be satisfied simultaneously. And in this work, we're trying to use different memory elements to satisfy both of them independent of each other. That's the key novelty. So we will use positive level latches to transfer the information and negative level latches to slow down the fast runners. At the end of this optimization phase, we will try to save some area because in integrated circuits, area is money. Roughly, the cost of an integrated circuit grows with the second or third power of the area. So if you save 10% of area or 5% of area, you easily save 40 or 20% of money in the end when you need to buy that circuit. So we will use flip-flops to recover area at the end. And very important, as I said, for every register that we had at the beginning, there will be a register in the same location at the end, enabling the use of standard tools. Very important because we don't want to create our own tools. We built an optimizer that drives existing place and route tools from Synopsys, Cadence, Mentor to do the right job under our constraints. But we only compute those constraints. We don't do the layout, we don't do logic synthesis, anything like that. So in general, we know that we use memory elements, flip-flops and latches to store data. And we also know that in theory, latches can achieve better performance. I will describe in a couple of slides what are the differences between the two design styles. Latches basically have more flexibility. A flip-flop is like a double door that you find at the entrance of a bank. You can only open one of the two doors, not both at the same time, so that anybody can walk in, close the door behind him or her, and then open the second one and walk inside the bank. This prevents people from running in and out at will and taking all the cash out if they want. So this is a flip-flop, and it provides a very simple methodology. You can just to control all the flip-flops together to let people in, let people out. And as long as they can go and they are able to go from one door to the next within one clock period, everybody's happy and the system works. But this is very rigid. Everybody has to work pretty much at the same pace. With latches, there is more freedom. With latches, there are two doors, but there is some length of a road, something to do in between two successive doors, and they still open alternately. But if you get to a door early, you can walk through it and do some more work on the other side if you are quick before the door, or vice versa. If you're a little bit slow, you can walk through it while it is open, and if you don't have too much work to do on the other side, you can still make it to the third door in time. So latches are more complex to use, but provide better performance. And we have been trying to work with the strength of the flip-flop based methodology and the flexibility of latch-based in this work. So this is basically the timing constraints of the flip-flops. Here you have the first double door. Here you have the path inside the bank where you have to fill forms, do some work. And here you have the exit door. And within one period, one person can be inside the bank, do their job, and then go out. And then the next period comes, new person comes in, does their job, and goes out. And this means that in order to keep everything running, as I said, synchronously, the time the person spends inside this logic here doing work has to be shorter than the clock period, because at the next clock edge, the person will be allowed and actually required to exit. And at the same time, we cannot have a person going through two doors in one clock cycle, because that would be a violation of the protocol. You'd be doing too much work in one clock period, and that would make the system not work as expected. Latch-based design will have an open latch here, an open door here for some time. There will be another open door here for some other time. They will never be open at the same time, otherwise people could just race through. But they can do time borrowing. So if they get here early, they can go through and start doing work on the other side, or vice versa, as I was mentioning. And this is called time borrowing. If you have a cyclic logic where you feed back on the input of your computation, you increment the register. For example, you do I equal y plus 1. Then whatever you borrow on this side, you must return immediately on the other side. If you are in an acyclic pipeline, like the execution pipeline of a microprocessor, you can be more flexible because you eventually have to pay back all that you borrowed, but it will be much later. And there are timing constraints that have to be satisfied, and there is very expensive, that are about $500,000 to $1 million per seat set of software tools that allow you to do that for circuits with billions, tens of billions of gates and billions of flip-flops. One problem that I didn't mention is that whenever you deal with latch-based systems, you don't have a single clock that is providing timing to every flip-flop in the circuit. You have to distribute two. One to the positive, one to this first set of latches and one to the second, one to the first, one to the second. And distributing two clocks with very little skew to every destination is an extremely difficult layer problem. It is already difficult with one clock tree. Sending the same clock edge so that it arrives at the same time to all the flops in the circuit is very difficult. Getting to do the same with two is not twice, it's probably 4 or 8 times as difficult, which means in practice, except for old times when people could spend months and years designing circuits with 10, 20, 30 flops, now the dominant design methodology is based on flip-flops, not on latches. There is another technique that I'm not going to cover in detail, which does not use the non-overlapping clocks that I was talking about earlier. It uses pulses. So instead of keeping one door closed when the first one is open and vice versa, you actually open them all simultaneously for a very short period of time in order to avoid people racing through two of them. This is on one side simpler, because you actually have to distribute one phase of the clock. All these edges, as you can see, are all aligned. The problem is that the opening time needs to be different for every latch. And this means that you have to have local pulse generators that generate these pulses from a single clock that are tuned for every specific latch to latch path. And that's a complete nightmare, not from the writing viewpoint, but from the viewpoint of generating short pulses with a very precise width. That's not something that is currently feasible. Seymour Cray in the Cray 1 used this technique, but that was decades ago, and at that time circuits were simple, clock frequencies were lower, and everything was easier. So to summarize, multi-clock latch-based solutions are very nice because they provide good timing improvement by allowing time borrowing. You don't have to balance exactly the delay of every logic stage in order to achieve good performance. In a pipeline or in any flip-flop based sequential circuit, the delay of every stage of every combinational logic block has to be exactly the same. And that is not easy to do in practice with complex systems. It's easy to do for an FIR filter, for example, because all the stages are the same, the logic is the same, easy. In a microprocessor, the first stage does instruction fetching, which is not too complex. The second one does instruction decoding, which is very complicated for a complicated instruction set. The third one reads the data, which is again simple. The fourth one does arithmetic computation, which again is computation intensive. So it's hard to balance those stages. So people use multi-clock based, where you can borrow time from an easy to compute stage to a hard to compute stage. However, we have problems in clock tree synthesis, as I was saying, when you need to lay out the wires physically on silicon. Pulse-based solutions use only one clock, but require precise pulses generated locally, which is difficult to do at high clock frequency. There is also a third way of doing things, which is you don't ask the designer to come up with very well-balanced pipeline stages. You ask the designer to come up with correct register transfer logic. And then in logic synthesis, or even during placement and routing, you start moving the flip-flops back and forth. If you have a flip-flop in front of, at the output of an AND gate, you can move it before the AND gate and it becomes two flip-flops. Logically, same functionality, timing is different. You have, in effect, borrowed some time, to use the terminology that I used earlier, from the input to the output. You have moved some delay, some complexity from the previous stage to the next stage, and you can do vice versa. Retiming is good because in terms of performance, it can improve significantly, as we will see near the end of this presentation, the performance of a circuit much beyond what a human designer can do. Not because humans are stupid, because they cannot keep track of billions of flip-flops. It's only a computer that can manage the position of these billions of flip-flops. The problem with retiming is that you cannot check that the result of your synthesis, placement, and routing of your digital circuit is correct. How can it be wrong if it is done by a computer, not by a human? Computers never make mistakes. Yes, but programmers who write the place and route software unwittingly introduce hundreds of thousands of bugs into that software, which means that the layout that you get at the end and that you'd like to send to fabrication in Taiwan or Korea, South Korea, of course, might have some bugs, some problems. And if you are unable to check before sending it to fabrication, you may end up putting a $10 million check on the table just to create the masks that will be needed to produce your circuit. And this is going to be very, very painful if the circuit comes back non-functional. It happens once, you'll get demoted. It happens twice, you start flipping burgers somewhere else. So you don't want to send out an unverified circuit. Retiming, unfortunately, makes equivalence checking that the RTL code that you wrote is equivalent to the layout that goes for fabrication, much, much, much harder. Theoretically solvable, but very, very, very hard. And as far as I know, to the best of my knowledge, not done in practice. Okay? Because moving registers is difficult. In practice, we can solve combinational equivalence checking. So if we keep the flip-flops in the same locations, we can check that the original RTL logic is equivalent to the logic extracted from the layout. If you start moving registers around, you need to do sequential equivalence checking, which is much, much harder. So all the techniques that I described to improve performance beyond what is allowed by keeping the flip-flops in the original positions have significant drawbacks. Here's where we come in. So what we are trying to do is start from a flip-flop based design created at the register transfer level by a designer, and then convert it into the most efficient, the most high-performance implementation we can. And we go through several phases. We start from a design with positive edge-triggered flip-flops everywhere, because this is the standard methodology. This is what every good digital designer knows how to implement, with combinational logic in between. And here we have an example of a very simple logic with a bunch of flip-flops at the input, bunch of flip-flops at the output, and several paths of different lengths between the flops of the launching stage and the capturing stage. You see that I have a very short path here, and a very long path here, and another short path here, and another short path here. You can say, well, this is contrived. No, this is just a full adder. This is an n-bit adder circuit, ultra simplified, but this is what adder circuits look like in practice. Multipliers are pretty much the same thing. So this is not a rare case. This is the common case. So the first thing we do is convert all the flip-flops into positive transparent latches. And as we saw before, this is good because it allows you to borrow time, because this is going to be open for a certain amount of time, not just when you walk in and go out. So there is not a strict timing constraint about when data have to have arrived here. It can be early, and then you have more time for computing on this side. Or it could be late, and then you can have less time to compute here, and you can balance things much more evenly. However, this circuit has problems with short paths. It is likely that somebody who goes through this fast path might be able to actually cross two levels of latches in one clock period, and that would be very bad, particularly if this depends on the logic delay, which is different from circuit to circuit. Because at that point, the functionality of your circuit might depend on when it was fabricated, how hot it is, and so on and so on. So it might work in cold weather and not in hot weather, or it might work today and not tomorrow, or it might work in this car and not in that car. That would not be good. So in order to get this circuit to work, we could use pulse clocks, as we saw earlier, but they have the problem that narrow pulses are difficult to generate. So here we get a new type of logic element, the negative triggered latches, level sensitive latches. And we use this to delay the launching of this signal here. So if we have something that goes too quickly through this couple of positive transparent latches, we insert a negative latch here, which would basically delay the output by half a clock cycle. This is like putting a long chain of buffers or a long wire that will delay. This is like giving a lot of work to do to the data going from here to here. However, putting the negative latch here is not a good idea. Because yes, you are slowing down this fast path. That's good, that's the intent. But you're also slowing down the slow path, which becomes even slower. So if you gained anything from the previous optimization converting into positive transparent latches, you are going to lose that big time because you have slowed down also the long path. That's not good. Same thing if you try to put it on the other hand. However, a very important property that was actually proved by a friend of mine, one of my best friends, when we were back in Berkeley, is that given any circuit with long and short path constraints, there is always a place where you can insert a delay in the short paths that will delay them enough to make them long enough and will not affect the long paths at all. That's the theory. That, of course, is if you can use ideal gates, ideal latches, and so on and so forth. But we will see we can fudge things at the end a little bit to make this hold also in practice.
Yeah, question.
Yes.
That thing holds if the delays are data dependent, value dependent?
Here I'm using static timing analysis. All that I'm going to do is completely pattern independent. Okay.
No,
So
the condition that you were saying for your fixing fault violations, that you can find a place to insert the buffer or delays, and will be data independent?
this would be data independent. Yes, absolutely. There's always some edge on every short path. There is some edge, some gate to gate or gate to float edge, which can be slowed down. And if you take enough of them, you will eventually be able to slow it down enough to meet the whole time constraints. Now, here, the result I'm quoting is not exactly the same thing as what we're doing here, because here we are not doing continuous slowing down. The result I was mentioning refers to when you're using logic or wires to slow down a signal. But conceptually, we can use something very, very similar here. We cannot achieve the same degree of optimality, but as we will see later, we can already improve performance quite a bit. Okay, so this is not as flexible. It is much less expensive because the problem of slowing down, instead of putting a negative latch here, we could put a couple of inverters or 4 inverters that would slow down the signal and not require, and they could be tuned much more finely. The problem is that they cause area increase. And as I said earlier, you don't want to increase the area of your circuit too much. So we will see that we want to limit the amount of area increase to something that is more or less linearly dependent with the increasing performance, because this is something people are already used to. You know that the area times delay product of your design is approximately a constant given a function that you want to implement. So something faster will also be larger, something smaller will also be slower, and between the two there is an approximately linear relationship. One times the other is equal more or less to a constant.
And another quick question.
Yes.
You never insert buffers on the clock. You could delay the clock.
Yes.
Locally.
Yes.
Why you are not doing that?
We are exploiting all of that. In fact, in the final layout phase, we are exploiting clock skew, smart clock skew, what's it called? I forgot. Anyway, inserting buffers on the clock, tuning the delays on the clock. We are exploiting, in some places, insertion of maybe a couple of inverters or doing routing a little bit longer to slow down some paths. So we are still exploiting that, which is an inherent capability of the layout tools and the logic synthesis tools that we're using. And in fact, the best results are obtained, thank you for the excellent question, are obtained when you combine these techniques. The negative latches is a big gap. You can use it to have a big improvement, a big increase in the delay of this signal with a relatively small amount of area. Inverters, routing, clock skew, adaptive clock skew is a smaller gun, much more precise, which can be used for the final tuning, and we exploit those. Okay? So these negative latches are used to meet hold time constraints, and we insert them in the places where they don't hurt performance. Finally, as a final area recovery step, we take pairs of negative latch, positive latch, which is equivalent to a master-slave flip-flop, and we merge them back, or positive latch, negative latch, equivalent to a negative edge flip-flop, merge them together in order to save area, because in practice, the layout of a flip-flop is smaller than the layout of two latches. So, first of all, if we do this, we achieve the ultimate performance at a potentially high cost, because we end up with more positive latch, negative latch pairs than we had in the beginning, and these are bigger than one flop. So we apply this only on the most critical paths, the ones that need to be taken care of. In this circuit, these are the two longest paths, and we would do the conversion into transparent latches only for the endpoints of the long paths, where we need to use time borrowing. That's the first thing.
So
yeah.
Sorry, I have a question.
No.
In the example on the bottom, the middle bottom.
Yeah.
Imagine I have an AND with an input wire. Now that AND, because it's close to the end, can create a fault violation because it can go very fast. But if I put so it's for some values can be a long path, for some values it's can be short path. But if I do that, I convert it to a latch, then how do I handle the case that some values could have been a fault violation?
If the circuit has been optimized to be redundant, then there is always a place to insert those slowdown buffers or latches. If the circuit is redundant, you need the redundancy because you need to have essentially each. By the way, we may need to insert these delays also on gate inputs, not just gate outputs. That might help.
Okay, so in the wire that is the AND.
Yeah, exactly. So we don't slow down each gate. We can slow down also input. Without that, we would not be able to achieve these results. Okay, so we do this exercise only partially, only on a certain percentage of the flip-flops, and very important, we don't transform the inputs and the outputs of our circuit, because the inputs and the outputs have a contract with other people designing the cache, designing the bus system. So the microprocessor will have a boundary that will be still implemented with flip-flops that satisfy the tight hold and setup constraints, because we don't want to change the boundary, only the inside. Okay, this has to be black box, not white box. This is the flow. Start from register transfer level, do logic synthesis, take the netlist after synthesis, replace all flops with latches, do a first optimization phase ignoring hold time constraints. So we optimize only for setup. We tell the logic synthesis tool, ignore hold time. Then we extract timing information. We do our magic that is going to be described in the next few slides, and then we add negative latches. This will fix most hold time violations. There will be still a small number, which will be which are small in magnitude, and those will be dealt with by the final place and route, which is able to fix those because they involve very little effort. So during this process, we use two graphs. One is a timing graph that represents every gate input, every gate output, every connection between gates, and which is annotated with three values. The first value is an estimation of what is the available slack time to complete the computation if we insert a negative latch in that position. And we want that slack to be always positive. We always want our customers in the bank to arrive at the end in front of the next double door or go through door, simple door, with enough time to be comfortable, not to be rushed. Or even worse, we don't want it to be with negative slack, which means he arrives late or she arrives late. Okay? So we want to have the estimated setup slack to be always positive for the selected locations where we insert those latches. But we compute that for every potential location. We have a graph where we compute, if I insert here, I get this. If I insert here, I get that. If I insert here, I get that. And then we use the information, which ones are not suitable to create the next type of graph.
Sorry,
Yeah.
So just the phase that column with the placement, insert blocks, management change the placement, so you can change the timing. How do you use that pre-placement, post-placement, or keep iterating? Or?
Until 6 months ago, we would be doing place and route before this step. And that turned out to be a bad idea, exactly for the reason you said, hey, we should talk afterwards. You understand this work probably better than I do. So that actually was intuitively reasonable. We thought that incremental place and route could work in this case because we are not changing the circuit too much. But in practice, it turned out to be false. So incremental place and route works only with smaller changes. It is meant to work when somebody changes from +1 to +2 or something like that. Not when you take maybe 1/3 of the flops and convert them into pairs of latches. So at the end, what we're doing is we use post-synthesis timing. We do optimization based on post-synthesis timing, which is less accurate, but we don't waste any time doing a very accurate job that we then throw away completely. And we let the final layout only to happen on the optimized netlist, not on the initial netlist. Once we have the set of insertion locations, which are forbidden because they have a negative, they would introduce a negative slack, and the set of locations where it is possible, where you have a positive slack, we create another graph which represents only the short paths. And we try to find on this graph a cut that breaks every short path with a negative latch, and which does not involve any case of insertion where it would create a negative slack at the end. So we basically select out of all these gates only those for which the insertion before the gate or after the gate does not lead to a negative slack, which would mean timing failure. You don't get through the gate, through the door at the next stage. So if we take the algorithm as I described it before, we end up in practice with too many negative latches, which are good for performance, but bad for area. And we don't want to pay too much in terms of area for too little gain in terms of performance. So in practice, we use a couple of derating factors. We basically accept solutions which would still lead to small negative slack, because we hope that the layout phase will be smart enough to speed up those paths. In fact, modern physical implementation tools do also logic synthesis and gate sizing on the fly during the place route phase in order to fix small timing violations. For those, we don't need to do the conversion into positive latches. Second optimization, we don't want to fix all the hold violations, because some of them can be fixed simply by buffering or routing through a longer route. Both of these are essential, and both of these introduce hyperparameters in the algorithm, which have to be tuned in order to reach the best trade-off between performance and area. If both these thresholds are too high, you end up having too many things to fix in the layout, and the layout may either fail completely or may require a lot of area increase to insert buffers, for example. If you take too small a value, then you end up with too many negative latches, which is too much area. So these are tunable parameters, like in any good layout system. You have to tune a few things. And these days, people come up with machine learning algorithms that can actually look at the design netlist and provide the best tuning for the various hyperparameters. These two plus all those that already exist.
Yeah, quick question. Do you apply to all the pipeline stages, because usually designs that tend to be unbalanced,
yeah,
and only 10 makes, you will get most of the benefit for the most critical balance region.
Yeah, that is the first step I mentioned. We only apply this to the critical flip-flops. Non-critical flip-flops, will let them be. So layout solves the small violations that are left. So this is the optimization algorithm. It is an integer linear programming formulation. We picked it because it is very flexible, very easy to model all the various aspects. So we insert and represent as linear constraints essentially all the constraints that I was mentioning, namely only connections from gate to gate can be slowed down. We cannot insert a latch in the middle of a gate. It's impossible physically, or I mean, it requires completely different technology gate implementation. We want to cut only edges with positive estimated slack, and we want to keep things not far from being balanced. We don't want to make things too unbalanced. We put everything together, and we get a linear program that, in fact, looks pretty much like a min-cut problem. Integer linear programming, in principle, is exponential complexity in terms of the number of variables you have to optimize against. That would be very bad. You cannot use ILP in general to solve any complex problems. But this is a special case in which we are almost modeling min-cut. Min-cut has algorithms that can solve it in polynomial time. As a result, the structure of the ILP is such that the ILP solver can converge fairly quickly to a solution in a time that is like 1,000th of the duration of the layout phase, a few seconds or even a few minutes, as opposed to hours for complex circuits. Okay, even for large circuits, we tried it on circuits that are entire microprocessors, for example. So this is the result. We have the position for the latches, which cuts all the paths and minimizes the area cost. So we tried to apply this to two different categories of circuits. One is the standard benchmarks. In order to publish in the logic synthesis or physical implementation domain, you need to take the set of existing benchmarks that have been around for decades. At this point, the first ISCAS benchmark, I think, was published in the 90s. And you have to show how well you're doing. This includes something that is either very small like here we have a circuit with only 18 flops, to something that is pretty large, about 10,000. We talked with people working at companies and so on, both on the IC design side, like Infineon and ST, and on the EDA side, like Cadence and Synopsys, and they told us, well, yeah, if you can handle something like 10,000 to 100,000 flops, we are happy with it. We do with optimization, single phase optimization, not partitioned optimization on circuits of that complexity. We're happy with that. And then, of course, everything can be speeded up after that. You always start with an IRT and then come up with smarter algorithms that approximate these results.
Is that number of flip-flops the total number of flip-flops on chip, or only the flip-flops?
This is called the benchmark. These are benchmarks that you can download from the network. They include sequential elements and Boolean gates, and they are just portions of circuits from IBM, from I think Intel, a bunch of companies.
But then you're just optimizing a subset of the critical parts.
Yes,
say, right?
yes,
And it's a smaller subset of the total. Yeah. Okay.
yes. In fact, if you want, I don't have it in this presentation, and I'm running out of time. But we have statistics on the gain that you can achieve versus the number of flops you are willing to convert.
Yeah,
there is a correlation, fairly simple correlation. So this is the result on these circuits. This on the x-axis, we have the increase in frequency. So this is 50% faster. And this is the increase in area, 2x larger. And as you can see, things are all over the place. It depends very much on the circuit. There is not one single behavior. But overall, we have a regression line that is more or less better than, it is linear, of course, because it is linear regression, but it has a better slope than what I was talking about earlier. So in order to get 50% increase in performance, you need to increase on average, let's say, by 20% the area, which is good. And on average, we get about 30% frequency increase. This is on relatively small, totally meaningless designs. And we notice that, of course, if they are acyclic, we get better results because time borrowing works very well with acyclic circuits. If only you have to get to the final destination within an hour, you can optimize things a lot along the path. While if you have to run in circles and make it on time at every lap, things are more difficult. So for cryptographic circuits, which are typically acyclic, we get excellent results. For things like small microprocessors, which are also in this benchmark, they are less exciting, but still, on average, we show improvement. There is only a few, there is none in which we worsen timing, obviously. We could just not convert anything. And there are some cases in which we actually decrease the area because positive latches are smaller than flip-flops. So if there is very balanced paths, like in these designs here, we don't need the negative latches. Then there is a more interesting for me example, which is to take a RISC-V design at ETH Zurich, or ETHK, as they say there, designed by Luca Benini's group, which was already optimized by hand by his excellent PhD and master students. We took it as a baseline, and it achieved essentially 333 megahertz on the fairly old technology that we had available at the time. I think it was, I forgot. I don't have the numbers. I don't want to make them up. So we applied the retiming, which can be done with the Cadence and Synopsys tools, and does not allow formal verification to be run. And we got a frequency improvement of about 33%, which is good. With mix and latch, we managed to get 500 megahertz, which is 50% instead of 33%. So it's better than what retiming can achieve. And if we apply it only on a fraction of the paths, we get the same performance improvement and much smaller increase. And if you want more precise results, go to the paper. Oh, no, sorry, you cannot get to the paper because it's still in publication, but it should come out in the next couple of weeks or so. Otherwise, Filippo Minella, who is the first author of this work, will not graduate, unfortunately. I wish him the best. And yeah, this is just animation for that. So this is a clock frequency sweep for the same RISC design. We went from a clock frequency, which is the original, 333, and we go up to 500. And for various techniques, we applied the optimization, and we provide information about the achievable performance and the power and area overhead. In fact, this is the more important one. Area is the first cost function for digital design. Frequency is a hard constraint. Here, I'm showing that we can improve it. In reality, it's defined by the system architects. If I cannot come up with a RISC that runs at 500 megahertz, they go and buy from someone else. ARM, for example, yes.
Do you do only typical or do you do corner cases too?
This is something my student can tell you. No, I believe him. I think he did a good job. For the next design, I can tell you. Next design, which is much smaller, but was done at a company, he did, I think, 4-corner analysis.
Because adding corners will significantly constrain how many you can add.
Yes, indeed. So I think in this case, he probably did only 1 corner, to be fair. But I would need to check. If you send me an email, I can ask him that. Yeah. Based on the results, I suspect it's single corner. So that means only either the fastest or the slowest or something, or the nominal, because out of all the possible speeds that the technology can run at under different fabrication conditions, different operating conditions, and so on. So area is the most important figure of merit. As you can see, when we apply, okay, the baseline is this. This is the original area. So if we apply mix and latch only on the worst parts, we can achieve at the same performance level a slightly smaller area than what you could normally. So you could, if you run at the same performance as the flip-flop based design, in this case, it is actually smaller. Not much, but smaller. And in general, mix and latch applied only to the worst parts has the overall best area versus clock frequency kind of curve. The original mix and latch, where you translate all the flops into positive latches, has particularly high frequencies, significant overhead. Retiming is not too far, but we are always better, and we extend by quite a bit the achievable performance. And power is pretty much tracking, because everything else being equal, area is what matters, is the capacitance. Here, voltage is the same, frequency is the same, so only capacitance can change. So these two curves are proportional to each other for a reason. Here, I think it's pretty much the same. Yeah, it's the same picture, just more comments that I made already in words. Formal verification is the ability to do equivalence checking to check that the final implementation is equivalent to the original. You have
Because I was expecting the power to be a little better. When you do the power estimation, do you do activity based?
Yes, it is activity based, and actually
the latches should reduce activity.
No, because they let glitches propagate. So the problem with glitches are unnecessary, unwanted transitions of the signal, which eventually are cancelled. So a signal goes up and then down. A circuit with flops has fewer of those because they cannot propagate through flip-flops. A flip-flops has one value per clock period. A latch output, when it is open, can go up and down, up and down, up and down, which means that actually the power consumption of mix and latch is slightly higher than retiming. But power is, regardless of all the green claims, only a secondary concern. Frequency and area are the two main ones. So with respect to formal verification, we use standard static analysis, static timing analysis tools to check the delays. They support all kinds of flip-flops and latches. They are actually the only tool in the chain that support that very well. because people can do these designs by hand. They don't know how to do it, most likely, but they can in principle, and so the tools support that. And then we use equivalence checking by using a trick, namely, we take the original circuit, this is the output, so we turn the register that are the replacement of the original ones into black boxes and tell the equivalence checker, look, these are exactly the same. Please check the combinational logic in between. Check that I didn't leave any open circuit or any short circuit during layout. Check that I didn't convert an AND gate into an OR gate by mistake during logic synthesis. And while doing so, please make sure that you treat these negative latches as buffers. So we insert some other gates that are considered as black boxes in here, and we declare them as transparent black boxes. So at this point, we check the combinational logic before, after the black boxes, and if everything is equal, equivalence checking is passed. Timing analysis will tell us if signals arrive on time. That's the first thing. Design for testability is another important constraint in practice. We need to be able to check after fabrications that our circuits work, because we don't want to sell bad ones to customers who might become upset if their car crashes or if their missile falls after launch. So the interesting thing, the key thing, is that we keep sequential elements at the original locations, which means that any test vectors, any values that need to be applied at the fabricated circuit on the test machine to check that the logic works will still be applicable also to the transformed circuit. We didn't touch the combinational logic. Second, for each positive latch, which does not allow standard scan-based testing, we can add a small shadow negative latch, which does not do anything in normal operation. It's just an overhead, but design for testability has an overhead. Even with regular flops, because you need to route the test clocks and so on. And this negative latch is used only in test mode to create the scan chain that allows you to push in all the test vectors, test the combinational logic, and get out all the values from those registers. So existing design for testability tools work also with mix and latch, at least the one from Synopsys. The one from Cadence doesn't, because nobody asked them. So if we're going to choose a Cadence to work with, they need to fix this. So we also work with a company that does chips for a living, Infineon. In particular, we have tight connection with the group in Villach in Austria. Nice skiing result, by the way. And they used our methodology on a very, very, very small circuit. It was just a proof of concept, just to show that the technique could be applied with a real industrial design flow, where you need to talk to real design engineers to get the setup, the technology, the methodology, the scripts, and so on and so forth. And it was not just applied, for example, in one corner instead of four, or whatever they chose to do. In the end, the clock frequency improvement is smaller than before, not only because of the corner-based mechanism, but because this is too small to actually have any unbalanced parts, so there wasn't much to optimize to begin with. So this was just a proof of concept. The PhD student who did the work is still with us, luckily. The first one is leaving, but we have a second one in the pipeline. We'll spend another 6 months at Infineon doing a more serious design, and then we will have probably something bigger to show. In conclusion, we have shown how to use all 4 sequential memory elements that you learned exist in digital design nature. Previously, you could use only 1 or 2 of them, or you knew how to use only 1 or 2 of them. We use all 4, and we use that to improve performance significantly on a fairly non-trivial design like a RISC-V core. We achieved 50% performance improvement, which is better than retiming and allows formal verification to be used without any problems. We have knobs to control the area overhead versus the performance improvement, and depending on the target frequency, you tune the knobs to allow you to get to that frequency with the minimum possible area overhead and power overhead. That's it. Any further questions?
Yeah, so when you're simulating different process corners or doing Monte Carlo, when you add in inverters into your clock path, or if you have to have extended wires to delay to introduce clock skew, does that have much effect on clock tree synthesis? Does it make it harder?
Yeah, of course.
Yeah.
And this is something I know nothing about.
Yeah.
I take placement and routing as a black box.
Yeah.
I teach how basic algorithms work, like I teach other things that I know little about, but I don't know anything about the details. I know that it is doable because people do it currently.
Yeah.
I mean, the layout problems that we are generating are not different from those that a regular place and route tool has to handle when dealing with a regular synchronous flip-flop based design. Nothing fancy or nothing more difficult. Unlike asynchronous circuits, which I worked with earlier, which are a little bit more difficult to handle. But these are still synchronous, and those tools know how to handle clock skew and so on, also with latches, not just with flip-flops on the place and route side. It's people who don't know how to design with them in the first place. People don't frequently mix latches and flip-flops in RTL designs. Sometimes they do, particularly at the boundary of the circuit when you deal with analog and so on, or when you want to optimize a long-distance communication. At that point, you might use those techniques for a few latches in the entire circuit, but not on a massive scale like we can do now.
So yeah, if you find yourself, or find himself changing how he approaches RTL and being more comfortable with perhaps having less combinational logic between flip-flops, because he knows that it's going to be optimized even further once doing mix and latch.
Sure.
Yeah.
That would speed up the design cycle.
Yeah.
I mean, you can always spend the same amount of time doing your RTL design, and then get better clock frequency, or spend less time and still get a decent frequency, the same one that you could have achieved by manual balancing of the stages in a shorter amount of time. That's always possible. Well, it works both ways, to shorten design cycle or improve performance at the same design effort.
Great.
Just like HLS, by the way, same thing.
Great. Yeah, if there's no other questions, then yeah, let's give Luciano another round of applause. Yeah, thanks for joining.
You deserve a cookie. That's very good questions.
Easy, man.